Another example, let's say a boy uh, jumps, well, maybe not jumps. A boy grabs onto a rope. Maybe this is boy Tarzan. Uh, Swinging down from a cliff. So I'm going to draw a picture here. So let's say we've got a little ledge here. Maybe this is a rope swing over the water. He's going to jump and dive into the water. There's a tree on the edge of the. There's a rope hanging. Maybe there's a tree right there. So the guy, this boy, grabs hold of the rope and swings, and he winds up somewhere over here. Uh, yeah. So the rope, we'll say, is 2.5 meters long, and at the bottom of his arc, the boy is traveling at 3.1 meters per second. We taking his initial velocity to be 0, what angle was the rope at initially? Okay, so you want to find, and you could give the angle from the vertical or the horizontal, either way. So we can apply conservation of energy to this situation. So initially, he's some height above where he wound up. So we'll make this point where he wound up our 0 for potential energy. So that means we have an initial gravitational potential energy. I said his initial velocity is 0, and then there's no spring in the problem, so we can ignore our 1/2 mv squared initial, and we can ignore all of our 1/2 kx squareds. And then he winds up with some speed, and we said that was the 0 potential energy, so we can ignore the gravitational potential energy term, and again, there's no spring. So we see that his initial height then is, well, we can solve for his initial height by plugging in numbers. You can say 9.8 h naught equals 1/2 3.1 squared, 0.5 times 3.1 squared divided by 9.8. We get that his initial height was 0.4903, etc. meters. Okay, so I've got that value, but now we got to figure out what that means about the angle of the rope. So his initial height right here was 0.4903. We know the length of the rope is 2.5, which means we can figure out from here to here, we can figure out what this is and make a right triangle here and use that to figure out what the angle is. So this height, we take 2.5 minus answer, we get that this height is about almost exactly 2 meters, 2.01 meters. And now we've got a right triangle where this, from here to here, is 2.01 meters. And we know that the rope is the same length whether it's horizontal or angled, so this is also 2.5 meters. So we have two sides of this right triangle. This angle is adjacent to 2.01 meters, and then 2.5 is the hypotenuse. So we can say cosine of that angle is equal to 2.00 whatever over 2.5, and then solve for theta. Take the inverse cosine of that value over 2.5, and we can say that the rope was then angled at 36 degrees from the vertical. Or if you had done it but finding the opposite angle, then you would wind up getting 54 degrees from the horizontal. And that would also be acceptable, of course. All right, I'm going to do one more example here. So let's say a mass of, I don't know, 35 grams is pressed down into a vertical spring with constant 110 newtons per meter. The spring is compressed 8.5 centimeters below its equilibrium position. And then my question is, how high above the equilibrium position of the spring does the mass reach when the mass is released? Again, we can apply our conservation of mechanical energy equation. Initially, we have some gravitational potential energy, we have some spring potential energy, but since it's pressed in and released, we don't have any kinetic energy. So this is initial position, so spring, mass, and then the equilibrium position of the spring is somewhere up here. I'm going to set my potential energy equal to 0 at this mark, because the question asks how high above this equilibrium position does the mass reach, so that's a good place to set as our 0. And then later on, the spring is released, and the mass flies up somewhere up here, and we want to know how high it goes. Well, when it reaches its highest point, we know from our studies of projectile motion that its velocity is 0 at that point. So at that highest point, we can say that it has some gravitational potential energy. It's no longer touching the spring, so it has no more spring potential energy, and it has no kinetic energy because it has come to rest. Now, some people think this is weird because obviously it was moving in between, but all the kinetic energy that it gained as it was started flying up then turns into potential energy up here. So we can do this in one equation. We don't need to do anything with the whatever kinetic energy it has in the middle of things happening. And then we can plug in numbers. 0.035 is mass, 9.8. Its initial height, well, we set our 0 at the equilibrium position of the spring, and this is pressed down to the spring, compressing at 8.5 centimeters, so we went 8.5 centimeters down, so that's negative 0.085 meters for our initial height. We got plus 1/2, k is 110, x naught squared, 0.085 squared. Since it's squared, it doesn't matter. You could plug in negative if you wanted to. And that's equal to g h final. And then we can algebra away. Take 0.035 times 9.8 times negative 0.085 plus 0.5 times 110 times 0.085 squared, divide by 0.035 times 9.8 with parentheses around it, and we get that the final height that it reaches is about equal to 1.1 meters, which might seem pretty high because it was only compressed 8.5 centimeters, but it flew up to 1.1 meters, but 110 newtons per meter is a pretty strong spring. So that works out. So these are all just different examples of how we can apply conservation of mechanical energy. Remember, we just take this big old equation that has all the possible energies that we've dealt with so far, plug in what's actually there, and then solve. And keep in mind, we can apply this if only gravity and spring forces are acting, at least of the forces that we know about so far. If there are any contact forces, pushing forces, if there's friction, if there's air resistance, then we can't apply the conservation of mechanical energy.